This is the last material before the midterm. I already assigned the problems, so there's not much to say. The homeworks, if you really look at them, they're mostly duality, so it's not really. You want what? Huh? Yeah, they're mostly duality, right? If you look through them in chapter 14. But I want to make them a little bit dirtier with some of the theory we're going to do, computing primal functions and stuff. Okay, anyway, so as requested a long time ago, I should have done this a long time ago. What's the geometric viewpoint of duality? So this is chapter 14. And so this week we'll go all in duality and one of the methods used there. Okay, so let's do that. Too loud. Way too loud. I don't like my voice. So, okay. So you start with this minimization problem, also called primal problem. And if you remember, the dual was you take your what is it? You take your f of x, and then you add a mu vector, right? So this guy is summation of mu i's with gi's, right? Good. This is not x star. This is, and we showed that you have weak duality always, but some of you didn't quite get it. In string duality, you need KKT. So I know you got full marks, but you should have checked the Hessian as well. Okay, so even the TA missed it. So I'm not gonna go through like rebugging, but for the midterm I will throw the full hammer. So make sure you learn your Hessian. Okay. So what am I doing? Yes, geometric point of view. So if you Google duality, you're gonna see some fancy pictures with hyperplanes and some curve. I'm gonna explain those pictures today so you know what's going on. We need the following object called primal function. This also goes under the name sensitivity analysis. Okay, so you had a homework from week 6. Do the last problem. Do last problem of 5.1 from the convex optimization. Okay, so we're gonna do this today. Anyway, so this is the primal function. And can anyone tell me what happens at omega 0? What do you get? What happens when z is 0? Yeah, I don't know. What happens when omega is, when you put z equals 0? I mean, I could talk to the wall, I don't mind, but I think it's nicer when people participate. So what happens when I put z equals 0? Perfect, thank you. So, yeah, so when z equals 0, you get the original problem. And in the picture is as follows. In 1D, you have this curve omega z, and when you hit the intercept of z equals 0, you get f star, which is the what you're looking for, okay? The minimization. All right. So now let's have a picture of duality. So again, you're in this graph of RZ over here. So, okay, RZ, and you have an intercept like this at C, all right? That's what this line represents in 1D. Now, suppose that X star is your minimizer, all right? Then you replaced infimum, right? There's no infimum, you just have this X star. So now let's see the picture. If I plug in my mu star, what happens? Let's do this carefully. So you're solving two problems. In the dual, you have a mu star, so that maximum of phi mu is equal to phi mu star, which we denote as phi star in the picture. This is from your textbook. Okay, so this picture. So this is the lower bound. And if you have strong duality, so if strong duality, then you have that phi star is equal to the maximum. So you have what I wrote there. I mean, this is the next picture. So, okay, let me do this first. So this guy is equal to phi mu star. Like this. So this is a z mu star plus r. So this line has phi star as its intercept. Okay, so now, what does that mean for you? If your primal function is not convex, then it will never touch the phi star, the f star. Okay, so you can see from the picture that strong duality is only when intercept is f star equal to phi star, right? Isn't that the intercept, the strong duality? Right? Only when these two are equal, you have strong duality. So from the picture, it means that the line has to touch the curve. But this cannot happen if it's not convex. Do you understand? So if you do not have local convexity, these two will not touch each other. So this is lack of local convexity, which is basically KKT. You understand? So for this line to be tangent to the primal function, you need local convexity, which is KKT. Okay, that's why KKT is if and only if. If you have KKT, you have strong duality. If not, you don't. Okay, good. So that's the picture. And then when you do have convexity locally with the Hessian, then you have strong duality. Okay, so this is KKT. So please remember to also look at the Hessian, right? Don't forget to do that. All right, let's do an example to give you an idea of all these objects. So this was your homework 5.1. And I'm gonna do the last part with the sensitivity. So make sure you understand it, because that's like a perfect midterm question, right? For you to do all the parts. So yeah, I think I will put one like this. What else can I put? I have nothing. I have this and rate. I have nothing to put in the midterm. So at least I'll have to put this stuff. All right, let's do this question carefully. All right. So you did this, whoever did it. And you have this function and you have this feasible set. So here's the picture. Okay. So the feasible set is this strip. Okay. This is the region where x minus 2, x minus 4 is less or equal than 0. Okay. Right? From 2 to 4. That's the region. And just from the picture, you can eyeball it to see that the minimizer happens over here. Okay, I don't need to do derivatives, Lagrange, or anything. Just from the picture, you can see that it hits it at the left corner. I should have asked you that. I'm talking too much. Okay, so now Lagrange dual. I am doing this because I want to find the dual problem and the primal function. So as always, you put your function plus the constraints times with the multiplier. Here's a nice picture I found. So as you vary lambda, you get different graphs of the Lagrange multipliers. So what's the, yeah, so this guy over here would be L of X of 1. Okay, so these are the different Lagrange multipliers. And why do we care about this? Because the minimizer will be the, will give you the dual function, right? So, but let's do it by hand. So when I take the gradient of this, so what is that? This is x squared plus 1 plus lambda x minus 2, x minus 4. Can someone eyeball it? What the what's the first term? Anybody? No, okay. I heard another voice besides being. Did you want to say? What? Then what do I put in? Is there a quick way to do it? You can do product rule, huh? You can do product rule. Just do product rule. Yeah, it's x minus 2 plus x minus 4. That's it. Product rule. Anyway, so this is your guy. And if I set this to 0, I get this. Okay, let me not do all the things. So you get this guy. Only for, maybe I should do it. Let's just do it. I want to show you why it doesn't work otherwise. Okay, so I have to do math. And then what's my constant? Minus 6 lambda, right? And then I isolate. So here's the problem. If you isolate, so you have 2, 1 plus lambda, right? Equal to 6 lambda. Yeah. Now I cannot divide unless lambda is not minus 1, right? And moreover, this guy is, I don't know, what's like, anyways, I cannot divide unless lambda is minus 1. Okay, let me just say that. And then, but then, so okay, that's why lambda cannot be minus 1. But what about lambda being less than minus 1? So maybe you can eyeball it. I'm not sure. So we had x squared plus 1, and suppose this is like minus 3. I don't know. Can you eyeball that this will become minus infinity? All right. How will I do it otherwise? Yeah, you have to do it this way. Otherwise, you can. So, oh, I know how to do this. This is easy. So here's how you prove. Well, I shouldn't have raised this. So this is the claim. All right. Let me prove it to you. Unless someone has an idea how to do it. I have a dirty way. How would you prove that? Do you know? All right, let's do it. So what you do is you have x squared plus 1, and then I have plus lambda x minus 2, x minus 4, right? Isolate the dominant term, which is 1 plus lambda x squared, and then lower order terms. Okay? What happens when 1 plus lambda is negative and x goes to plus infinity? this guy goes to minus infinity, right? But it's x squared, so it doesn't matter whether you go plus infinity or minus infinity. This guy always is minus infinity. So here's how you argue this. So you have minus 1 plus lambda x squared, and then lower order terms. And then they ask you, find the minimizer. Well, if you force me to have this guy to be negative, then the minimizer is I can take x squared either direction, just to infinity. Because remember, at infinity, the leading order is what matters, right? So I don't know if you remember this from calculus. Whenever you have a polynomial Pn of x, its limit as x goes to infinity is equal to the limit of its top coefficient. Is that okay? Do you remember? Yeah, okay, that's all I'm using. There's nothing fancy here. Okay, good. I'm happy. That's great. Everybody happy? All right. So that's how you get your constraint for the dual problem. And here's my dual function. My dual function is this crazy looking rational guy, and here's its plot. And so can someone tell me if the dual problem has a solution? And which one is it? From your eyeballs. Can I go up? I don't know how to go up. Yeah, can you eyeball it? I can eyeball it. Isn't it 1? Maybe it's 2. No, 2 is too far, right? I don't know. Maybe you're right. I have no idea. But it has a solution, and I computed in the next slide by hand. Anyways, so question, yes. Yeah. Yep. Yep. Perfect. So the dual problem is maximize that guy for lambda bigger than -1, and I ignored less than -1 where it's minus infinity. All right. So what's the optimum? The optimum is, isn't it beautiful? You turned it into 1D. I mean, it was always 1D. Okay, later on I have a 2D to 1. I take derivative and then of this crazy guy. And if you do that, then you set it to 0, you get the solution equal 2, which is what you said. And then you plug 2 back into your function and you get 5. And I think I talked about this. I didn't talk about it. Oh, yeah, I said you can eyeball it. So you can eyeball that the minimizer is 2. So if you plug it in, you get 2 squared plus 1, which is 5. So this is F star, okay? And then, is that okay? And then for the dual problem, you take its derivative. I'm not going to do it. It's disgusting. You set it to 0, and you get again 2, and which is 5 if you plug it in. So you have strong duality. Okay. Right. Good. Yes, we do. Oh, I have to prove it. Well, I mean, okay, you do have strong duality because I computed it by hand, but in other settings, maybe you only have existence of a minimizer, not a concrete one. But so I might as well do it. So here's your Lagrange dual, and by KKT, you need this guy to have a positive derivative, and I take it, and it becomes 2 1 plus lambda, which we said is positive, because we took our lambda to be bigger than -1. Okay? Great. All right, what else? Yeah, now let's come back to our primal function. So this is part of the homework that you were not assigned, but it's good to go review it, please. Okay. So this is the primal function. Instead of having 0, so omega 0 is the original primal problem, right? We talked about this. And I'm going to plot this for you. So try to understand what's happening, because this is a nice question to have. So I'm trying to compute this in Phenom for general U, all right? So I have to split cases. You'll see why in a second. So I split that on U minus 1 because I know this function from the plot. Where is it? Over here. I know that the x minus 2x minus 4 is has a minimizer over here that is above minus 1. And so yeah, so because the minimizer is minus 1, we have that u x minus 2, x minus 4 is impossible. Okay, so you ignore this, meaning the primal function does not attain values for u, less than minus 1. So in this case, you can say this is the trivial function, and you can set it to 1. So you'll see a picture in a second. Now we look at the other case. This is interesting. So how do I find the feasible set? I simply solved. I think I mentioned it today. Yeah. So these bounds. Let me draw them in for you. 3 minus 1 plus u, and 3 plus 1 plus u. Okay. And this is the function. It does something like this. And this is the function x minus 2, x minus 4, minus u. Okay. All right. So that's and you want the feasible set. So the feasible set is over here. This is the place where it's negative. All right, good. Now let's go back to our x squared plus 1, which is at 0, it's 1. So it's like this. Yeah, so you see x0, right? So the moment the feasible set is on the left of 0. So suppose you're in this situation. Okay, what's the minimizer for the function x squared plus 1? Yeah, so it's over here. So then you're done. There is nothing interesting there. So it's always 1, but then, which I thought, okay, fine. But then in the other case, again, from your graph, what happens is this is the feasible set. Okay. And in here again, what's the minimizer? Someone else besides minimizer? Who's the minimizer for this function? Huh? Yeah, you see? I don't know why, like, who am I talking to? X squared plus 1. No. That's funny. I mean, it's even in the slide, but it's kind of ridiculous. Yeah. That's because the feasible set is this blue guy. So you're only looking inside here, and just from eyeballing it, this is the smallest guy. Yeah. Maybe I should go slower. I don't know. What can I do? Anyway, so you plug in these ranges and you plug in your minimizers, and this is your this is plus infinity. Minus. Whatever. We'll see in the picture. Yeah, this is the function, and here's the picture. So the moment you hit 8, you become 1, constant 1. And the moment you hit -1, which is not even in the picture, you blow up to plus infinity. Okay? So this is the primal function. And let me ask you, what does the intercept represent? So what happens when u is 0? What do you think? What was the primal function? It was pu equal to the minimum of your guy, given that g is less than u. What happens when you put u equals 0? What? Yeah, so you get f star. So the intercept is just f star. Okay. And anyways, whatever. Yeah, okay. Yeah. Yes. And locally, you have a local convexity, like we talked before, from the picture. So you have, yes, you have a strong duality because locally it's convex. So you can come in from below with a dual, and this is the dual guy, and this is the dual maximizer. Okay, so at u equals 0 is where the graph hits the f star, and then this line, it's the maximization. So you have f star is equal to phi star, the dual. Okay, does that make any sense? All right. If you like, we call it pi star 0. I know there's so many notations, but the books have like, so I want you to have all the notations, like Thanos, like have all the rings and all the, yes, so that you don't get lost. Because, anyways, so here are all the notes, all the, yes. All right, fine, let's come back to reality. So, numerically speaking, you want to find f star. So if you eyeball the picture, you just want to find an intercept, right? So to find f star, starting with some nice picture like this that hits at some guy f star, the graph. Then you move your slopes around till you hit your graph. Okay, so this is basically called dual methods. So think of it as like different intercepts, right? So you go up. If you took 236, this is the parallel method. where you had a simplex and you came in and you hit one of the vertices, this is the exact same thing. Okay, the nonlinear version. All right. We'll explore two methods: steepest descent and augmented Lagrangian. These form, I mean, these are not modern methods, they're from the 80s. But what happens is people have put other pieces on them. So at the base, you have these guys, and then people just move them around and shake them and combine them. So if you start Googling optimization methods, you're going to find like a huge family, but these are the base. All right. Let's start with one that you're familiar with. So steepest ascent, because it's similar to steepest descent. The dual problem is to maximize, right? So what does the gradient of a function point to? Can someone tell me? Huh? Sure, yeah. So yeah, the direction of greatest I don't know what I mean, yeah, whatever, greatest increase. So you have your guy, this is 0, and anything that points away from the minimizer, for example, will be your gradient, how it looks like, right? Okay, so that means that where is it? So to do numerics, we need to study steepest ascent. So now you have the step changes by one little thing. So can anybody tell me what's the change with steepest descent? Huh? Yeah, perfect. So that's all, nothing else. So all the theory is the same up to a minus sign. Okay, so we can use all our results from before. And so you see, instead of having max, I have AK. By the way, this is completely meaningless, this AK, because of course I want the max. Okay, give it to me. Like the computer will ask me, what is the max? So often this is where the trouble comes in. They are very hard to find. They are costly to find. People have all kinds of methods. If you read that Burchaka's book, he goes into it page after page, trying to find these step sizes. Because really, that's the meat of the method. Good. How fast does this method converge? So we didn't talk about this, and I hope we will come back to it because you need machinery from calculus of variations. So if the next 3 weeks is calculus of variations. So you will get really advanced really fast. And I hope that you will have some patience to do this rate theorem. So here's the theorem. It's in your main book. Suppose you know that you have a minimizer. So you know there is something to find. Then again, take large and biggest of the following Hessian. So this is the Hessian of the Lagrangian. Then we have the following rates. Now you might say, didn't we do this last week? Can someone tell me what's so special about this theorem? Why is it special? Why is it not exactly what we did last week? Zoom people, do you know why? Anybody from Zoom, do you know? Is anybody there? I don't know. Any guesses? What? Yes. Oh, there isn't? Was it? What was it? No. But when you solve the recursion, you get 2k. Yeah. Oh, and then, oh, but thank you. It should be like f of x1 minus f of x. Yeah. No, the difference is f is non-linear. This works for any f. Yeah, it's insane. So that's why I need fancy tools to prove it for you. This could be anything. Like it's crazy. So I mean, we talked about this on the first week. You asked me about the eigenvalue. Why do I like the smallest eigenvalue? And this is why, because it gives me this rate of convergence. So you Taylor expand, right? So you have f of x star, gradient, and Hessian, and anyway, so and then you ignore the other terms, and the point is, this is roughly looking like a quadratic form because this guy is 0 by stationarity, right? So you're just left with this quadratic form. So you have f of x star x is equal to this Hessian, right? So it's basically like quadratic form with some correction. Is that okay, roughly? All right, good. So that's why it's the same thing, because you can show that this error from the Taylor expansion doesn't affect the rate. That's all. But to prove it, oh my God. All right. And the reason it's hard is because you're not working on a nice surface. This is like a weird called manifold. And you have to move the gradient descent along this crazy looking object. So that's why I need a lot of machinery. All right, let's come back. So this is the theorem. You're free to use it, okay? Namely, the steepest descent or ascent is given by this rate. And so coming back to our guy, so I need to find the rate of, I need to find the eigenvalues for phi lambda. Oh yeah, before that, I need to finally justify why you learned the implicit function theorem. So here's why. Once you minimize your problem, right? So remember, you spend all this time. This is given by some L of x star, right? And usually x star is a function of lambda. Like, I don't know. What's a bad, yeah. Something like this, right? Remember, whenever you find a minimizer in the Lagrange multipliers, you get it that it's a function of lambda, right? So, but let's prove that. Let's prove that this is the case. That yes, it's always a function of lambda. It's not a priori clear. So here's how you do it. Remember, the way you get your solution is you set your Lagrangian dual equal to 0, right? This is the x of x lambda equals 0. And yeah, and if you remember, this gives you a system of equations, okay? So I wish I had the theorem. Okay, whatever. So the implicit function theorem said that given a system of equations, if you have the following Jacobian to be non-zero, then you have that x can be expressed as a function of lambda. Namely, here's a crazy picture. Suppose this circle is the f of x lambda equals 0. Okay, So this is lambda, this is x. And it says that locally around the minimizer, so let me do it. What's a good picture? Let me do something crazy like this. Okay, yeah, that's good. It says that locally around the minimizer, so x star, lambda star, okay? Around the minimizer x star lambda star, you can write a graph for lambda. Okay, so why is this cool? Because it says that x of lambda for lambda close to lambda star are all minimizers. Okay, so that means that what I wrote over here. Okay, so as you move lambda around, you get a continuously changing minimizer. Didn't I do this before? Yeah, I did. Let me go back to my example. So we don't talk in generalities. Yeah, so before, right? I solved my stationary problem and I got a minimizer, and this minimizer depends on lambda. That's all I'm proving, right? I'm proving that you're able to do this. Okay, good. All right, let's go back. All right, anyhow, so and it's not zero by KKT. So KKT says that if you have X star to be a minimizer, then you know that the Hessian is strictly positive, right? KKT? Is that what it is? All right. Okay, what else to talk about? All right. Again, the question was find the rate of convergence of steepest descent for the dual problem. Okay, so again, I'm applying steepest descent to the dual problem. So I need to find the rate, but to find the rate, I need the Hessian of the dual, right? Is that okay? Let me repeat. We are doing steepest descent for a maximum over lambda of phi lambda. And so I need the Hessian. So to find the rate, I need the Hessian, and then by Thursday, I will give you the eigenvalues of this matrix. This is all in your book. This is not, so, yeah. All right, so let's start with this. And then, yeah. So first, we need to compute the gradient. It's a nice little question. So, so I use product rule. So what happened here? The gradient of f of x lambda is equal to the gradient of f of x times the gradient of f of x lambda. Is that okay? Chain rule? I'll wait. Is that okay? Yes. What? What? Is it okay? Yeah. So are you, no, I'm doing it step by step. Are you okay with the chain rule? Okay, good. Then that's step one. That's how I got this term. That's how I got the second term. And then the last term, I did product rule. So I did lambda of h. So I get lambda times gradient of h plus 1 times x of lambda, right? So it's 1. Is that okay? So that's how I got the constant term. And then this guy, I did chain rule again. So I got lambda h times the gradient of x lambda. Okay. So 1, 1, 2, 2. Is that okay? All right, good. Now, what do I want to talk about? Oh, yes. So then can someone tell me why this guy over here is 0? The guy in the parentheses? That might be a bit too advanced, but I just want to see. Is it too advanced? Okay, maybe it's. So let me remind you the implicit function theorem. It says that if you have a guy like lambda x equaling 0, and you know that gradient in x is not 0, then there exists lambda x lambda function such that f of lambda x of lambda is 0. This is the implicit function theorem. Okay. So any guess why the guy in the parenthesis is 0? Who's my f? Zoom? Anybody? Andrew? Daniel? Right. So it would be delta x of f of x plus lambda of h of x. Are these people even here? Oh, F stuff. Okay, thank you, Daniel. Good. Okay, I have to name people. That's how it works. It's like first aid. You have to tell them. So this guy is 0. So you're left only with h, which is beautiful. This is general stuff, right? So this is the gradient of your dual function is equal to the constraint. Is that crazy? Like, think about this for a second. Like, the dual guy isolated the constraint. I think that's beautiful. I like it. So if this guy is negative, it says the gradient of the dual is negative. There's a lot of cool stuff here. All right, moving on. Now I need to compute the Hessian, so I take derivative again, and then I just apply chain rule. Okay. So that's my Hessian. All right. I'm not done because this guy over here, x lambda, is meaningless. I mean, I have to put some information for this, and I will compute this explicitly for you. All right. So again, yeah, the Lagrangian. So we know by implicit function theorem that this guy is 0. Okay, so this is, I'm using it on the step over here. So I'm using that again. And the reason is, right, yeah. So I take Hessian of this again, I mean gradient. So take gradient of this whole thing. And if you do that, you get this crazy looking object. But this is cool because now you isolated the gradient of x lambda, right? Again, so we are trying to compute the Hessian of the dual. And we using implicit function theorem, we found that it equals the gradient of the constraint times the gradient of the minimizer perturbed. So now I need to find the gradient of the minimizer perturbed. And yeah, let me tell you how to finish from here. So you have lambda x lambda is equal to minus gradient of h. And then how can I isolate for this guy? What should I do? Linear algebra. Actually, maybe, huh? Yeah, so you have this guy inverse. Okay, so this is where the inverse comes from. You're gonna see it so many times, you're gonna hate it, but this is where it came from. All right, so we found the Hessian. Do I say more? Yeah, so this is the Hessian of the dual, all right? Beautiful formula. You might see it if you go into numerics or optimization or machine learning or whatever. That's the guy. So namely, these are the constraints. And this guy is the Lagrangian dual. So L, remember it was f of x plus lambda of h. Good, but you take its inverse, that's bad. That's really, really bad. So that's why people don't really use this method, because you have to invert, and it's disgusting. It costs a lot of energy. Okay, here's a nice linear algebra question. So, so it's a minimizer. So by KKT, you get this strict positivity. But can someone tell me, using linear algebra mastery and wisdom, can someone tell me why the inverse is also a positive definite? Daniel, Andrew, Binray, Yumin, Rahman. And what's your name? First name. UN? UN? Okay. So this is linear algebra, bringing back good memories. There's no optimization here. Huh? 1 over what? Oh, yes, yes, perfect. Wait, no. Oh, yeah, you could do this that way, yeah. But what do you want to do? I mean, are you talking about the determinant of the inverse? Yeah, but like, let's say this is like a million by a million. How would you, no, but that's not product of the, yeah, sure, but that's not positive definite, right? I didn't say invertible. Invertible, you look at determinant. The question is, why is it, you know, yeah, why is it positive definite? There's a very quick and dirty way. I just want to see if you find it. It's very quick. It's like one line. The determinant depends on, but it's, yeah, I can give you, can you just give me a minute? I have to figure out one. So he wants me to find a guy who's like positive determinant, but is negative definite. Oh, yeah, here. 1 minus 1 minus 1. Yeah. This guy has positive determinant. And it's not positive definite. Huh? Look at what? Yes. So what's the eigenvalue? Yeah, that's it. So if you have A equal lambda V, then you have A inverse equal to what? So I have to do some stupid stuff. So from here, take inverse of both sides. So you have V equal to A inverse lambda V. Matrices are linear. So you get 1 over lambda V is equal to A inverse B. And so since lambda I are positive, you get that 1 over lambda I is also positive. Okay, good. Yeah, you get beat by human. It's good. Thank you, Daniel. It's great. Oh yeah, let's take a break. Too long. I'm tired. What is in for what? Let's see, what's 927? I'm sorry. Uh, so what happened with- Yeah. All right, fine. So cosine and then what is part? Oh, nobody's species are proposed. Uh, and then okay, sorry, what were you saying? Oh, you can. Wow, that's very impressive. Oh, I see, I see. Wow. Oh, yeah. Terrible. So then when did you get, oh yeah, so from here it's done, right? Oh no, it's not done. What the hell is done? Okay, there's no issue. Yeah. Do you have to switch? No, but it doesn't square. No, I know it's square, but once you find the. Because the square comes at the end. I mean, you have this left side. Right. What if you take race? What if you pull out? What if you like pull out the 8? Yeah. What happens then? That's what we're doing. I do have a shape of the board. It doesn't have. Are you sure there's no mistake there? But how come he doesn't have a shape? No, but for the things. So, what do you have minus? What is wrong? It doesn't have wrong. Yeah, it doesn't have lambda. Is lambda in some range? Like, what the hell is lambda? Well, lambda reactive times. Um, more like page down. It doesn't work. Steve Jobs. Oh, right. Can you not, can you take your maximum? Can you, yes, for my photo? If I take maximum of lambda, what happens to this guy? When is this guy the biggest? I'm not, like, I don't know, I think it's like when it's the smallest, right? Like yeah. Yeah, so this guy, 8 plus 8, 8 to 8 minus 200. When is it the biggest? What should lambda be to maximize the biggest? Lambda, right? It goes between smallest state and biggest state. So, who of the two? Yeah, because like if you take the smallest, you're removing less. So then this cancels out, becomes k minus 1, which is strange. This choice there's too many k's. Oh, no. Yeah. How come there's no powers? Yeah. Like even here. I see, yeah. I don't go from outside there. How can you live without pre-job? So you're saying this is a minus. Why did you look at inside? Oh, I think I know. No, I mean, what is it here? Can I see? Yeah, 1 2. For 12, yeah. I mean, how do you not in the book, checks usually like when there's a message sign. Yeah. Does this work or? I don't know. All right. What is going on? Yeah. So here's some beautiful stuff. We found the Hessian of the dual, and you might be asking, how do you know that KKT applies to it? And remember, KKT for maximum is the same up to a minus sign. So, like Yiming said, the inverse is positive definite. And so what can we conclude about the Hessian of the dual? What do you think? What's your guess? Just a guess. We show that it's positive definite. So it's negative definite. Good, thank you. So that means by KKT, so by KKT, you have existence, okay? Of the dual problem. All right, good. And we'll do this by Thursday. We'll get that the convergence rate depends on the eigenvalues of the Hessian, because as Yuming said, the top and the biggest eigenvalue of the inverse. So I don't know how to write it. U1 will be 1 over lambda n, and UN will be 1 over lambda 1. And lambda 1, lambda n are eigenvalues of Hessian Lagrangian, right? Good. All right. All right. So now let's do a nice example. So this is the primal problem, and you have a single constraint. Any ideas what this constraint looks like? So you can eyeball it. Centered around what? Which is over here. And is the radius 5 or? Yeah, that's right, that's right. Because when you put 0, you get, yeah. So this would be, who wins? I don't know. Does this guy win? Huh? What is square root 5? This is less than, it's less than 9, which is 3. Okay, good. That's great. So that means you're positive. So you have 3 minus square root 5, 3, and 3 plus square root 5. So this is your feasible set. And the minus xy, I don't know. Can I eyeball it? So minus xy equal to c. So that means y is equal to minus c over x. And if it's not 0, so what is that? These 2 lines, right? So when y is positive, x is negative. So I can ask you, but yeah. What do you think? Which quadrants? 1, 2, 3, 4. Huh? What? And what else? I mean, huh? Oh, I see what you're saying. Yeah. Of course, yeah. It also depends on what C is. So this is a mess. I'm assuming, I don't know, whatever. When C is positive, yeah, you get this. So it's kind of stupid. You just have the intersection. That would be the minimizer. But anyways, let's do some, because yeah, I mean, whatever. Okay. First, you need to do KKT. And if you do that, you get the following system, right? So let me do this for you. So you have gradient of f plus lambda h equal to 0. And so, yeah, so you have gradient of minus xy. Do I have to write it? X minus 3 squared plus y squared minus 5. If you take derivative in x, you get minus y. And from here, you get 2x minus 3. Yeah, that's how you get the 2x minus 6. Okay? All right. So you get this system and you use your active constraint. It's always active. So we're doing the baby case. I hope we'll do inequality on Thursday, which is harder. Yes, so you use these 3 equations and you get the intersection point that we talked about. Would just be, so let me put this in actually. So if you put 4 and 2, you get minus 8. So that means C is negative. So that means what? So, huh? So, okay, it was 3. And is 4 bigger than 3 plus square root 5? No, the other way, right? I mean, otherwise it wouldn't work. Okay. 4 into anyway, so it's here. So apparently, I don't know how it's even possible. It should do something crazy. That doesn't make sense. This is 4, and this is 2. And then our guy was minus xy equaling c, right? And now c is what? No, I'm trying to draw their intersection. So it's like y, what? So is it like this? Oh yeah, otherwise it will have 2 intersections. You're right. Thank you. Good thing to have some not stupid people like me over here. Yes. All right, good. Okay, great. That's great. But then, yeah, to have KKT, you need to check Hessian. So please remember that. People didn't do it. So please remember. So that means I compute the Hessian of this guy, and you can just eyeball it. Here's my 2, here's my minus 1, here's my 2, here's my minus 1. Okay? Is that okay? So that's how I get the, yeah. And can someone tell me why this guy is positive definite? In 2 by 2, it's easy. So can someone tell me why? Besides being Rui? Because you should know this. Zoom people, anybody, can someone tell me why this is positive definite? Daniel, Andrew, who else? Well, is that Mo? That's Mo, right? Okay. Hey, Mo. Determinant, determinant, and determinant of who? Oh, yeah, exactly, yeah. So you have 1 minor, and you have determinant of this matrix is 4 minus 1, so 3. What do you think is the rate? Yeah, it's harder. Let me do it. I mean, I didn't even talk about it. Okay. So yeah, there's a formula for finding eigenvalues. Do you know it? Should I? Okay. So the formula is lambda. Oh, you know it? Doesn't anybody know it? Huh? So it's a trace of the matrix lambda plus determinant of the matrix. I'm writing this because you need it for the final. There's no Wolfram alpha. Maybe in the future. Maybe I should let you have Wolfram alpha. Why not? Who cares? All right. Good. Lambda square minus 4 lambda and then 3. Yeah. And I'm not gonna. Maybe even I have to use Wolfram alpha. What? Sorry, what? How do you know? I have no idea what you mean, but like, oh yeah, what? You sound like Joe Nash. Let me. Okay, so and you found it by eyeballing its product and summation. Is that it? Yeah. I have no idea how you did. I can't, my brain is, so this is product of of the roots or, oh yeah, roots. Oh, I see, I see. Yes, yes, yes. Oh yeah, right. Yeah, that's right. But the trace is a little bit harder. It's not always the eigenvalue. Okay, anyways, whatever. Um, yes, okay. So since the leading minors are positive, yes. Okay, so yeah, the rate, you have 1 and 3. So the rate will be 3 minus 1 and 3 plus 1. So 2 over 4, so 1/2. Okay, good. Yeah, I know there's squares and everything, though. That's all I care about. All right. So now that we have KKT, we talked about we have strong duality. So that means the dual problem is equal to the minimizer, okay? That's strong duality over here. So actually, I might as well. So we found the point. It was 4, 2. Oh, I said -8, right? Yeah. Okay, good. So I'm supposed to get a moment of truth that this guy is that the guy on the over here will equal -8 by strong duality. Let me do it like this: f of star, which is -8. Okay, I'll do this by hand. I will compute this stuff. All right, let's do it. Again, you set your gradient to 0, and you get your 4, 2. So then I plug in my 4, 2 into my dual. All right. So remember, my dual guy is equal to the infimum of the Lagrangian. Okay. So you plug it in, and you get this horrible looking dual function. And apparently, the maximum of that should be -8. So let's do it. So yeah, anyhow. And okay, what else do I want to talk about? Yeah, so I have to verify my maximizer. So first I should say one thing. To find this lambda star 1, unfortunately, you will have to do phi lambda of f lambda equals 0. And it will give you lambda star equal 1. I mean, do not do this. Like, that's the whole point of duality. Sometimes a disgusting problem is easier, right? But you understand? So, what? Is that okay? I mean, I'm not going to do this because it's terrible. I know that this is the value from from the uh, from the primal problem. So that's how I know lambda is 1, and I expect you to just do the same. Do not take derivatives and kill yourself over it. So you just need to prove strong duality, though. Otherwise, you cannot use it. So that's why I'm allowed to use this, because I have strong duality. Anyhow, so but I have to verify it. So then, what do? I use my formula for the Hessian that we spend so much time computing. And again, you're free to use this. Okay, you don't have to prove it. So if we ask you, give us the Hessian of the dual, just use the formula. Okay, do not try to compute this. This is not reasonable within like the time you will have. So just use the formula. So I'll do this with you now. So H is equal to x minus 3 plus y squared minus 5. And I take its, yeah, let me ask you, I'm tired. My voice is getting lost. What's the gradient of this H? To what? Yeah. 2y, perfect. So then at the minimizer of 4, 2, you get 2, 2. Okay? No? You probably not. No, you do, no? Yeah. Wait, no? No, you don't. Yeah, you do. What? You do. 2 times 4 is 8. 2 times 2 is 4. uh, all right. It is 4. Where did I get this? This is not mine, though. That's weird. Are you sure? Yes, it is 2. Yeah. That's weird. Because this is not mine. And I do get -8, which is very bizarre. So wait. Yeah, I know. It's not the same thing. Something else. All right, fine. So forget this and put 4 and let's do it. So 2, 1, 1, 2, and then forget the 2. So then what do you get? You get 2, you get 4, right? And then you get 4. Yeah? Is that okay? Okay, and then what? 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 2, 1, and 1, 2. It's 4, right? Oh, it's 5. Yeah. Okay, good. I was testing you. And then we have 1, 2, and 4, 5. So this is 4, 14. All right. So then we have a bunch of stuff. We have 4 times 3, right? And then 14. Right? Because I took out the 2. So instead of 2, 4, I wrote, what am I talking about? 4 over 3, like this. Because I took out the 2, so I wrote it as 1, 2 from both. Yeah? Okay, good. And then you get this number, which is negative, which is all I care about anyhow. Okay? All right. So it's negative, definite, so you have a maximizer, which is KKT. All right, so, okay. All right. So we did this example in detail. All right, now finally, let's start talking about the other method, which is more widely used as a base. Like they were saying, it has some revival, but it's not, anyways. If you're really interested and you come back to it, look up alternating LAM. Okay, this is apparently being used. If you go to the Wikipedia page, that's the one they say people are using now in terms of this method. All right. So here's the Augmented Lagrangian. Even though it's not used as much as other methods, it contains the foundation for many methods. So can you tell me what's the difference with Lagrangian? What exactly did we change? There's a slight change. What is it? Huh? Right, so there's one more term, and this is called the penalty term. And why do you include this? Because you don't want to have a constraint. So This is a nice technique in optimization where you turn a constraint problem into an unconstrained. Because why? If I take C to infinity and I want to minimize this function, how can this work? Yeah, so that's a way where you can make your life easy and forget about constraint optimization and work with unconstrained optimization. So this, I mean, well, we could spend a whole month talking about penalty and barrier methods, but they're all about that you forget about constraint optimization and you go into unconstrained, which is a second year calculus. Okay. So yeah, this is called the Augmented Lagrangian. And this C will show up later on when we get the rate. But here's the heuristic, is that consider the same problem, but now add your penalty. So let me ask you, do you think this has the same minimizer as minimum f of x? Yes or no? Yes, because this guy is equal to 0. Okay, so I know it's stupid, but the point is you do this, then later on you forget the constraint. Okay, but you have to start from somewhere. Okay, good. All right, so let's do an example of computing this Lagrangian, augmented Lagrangian. Same problem. Actually, no, you haven't seen this. I've seen it hundreds of times. So you have this primal problem, and again, you eyeball it. So you have, it says set x to be 1, which is stupid, right? So you have 1 over 2, and then you take minimum over y. So then what's the minimum over y? Yeah, this is the smallest when it hits 0. So you get 1 plus 0, 2. So the minimizer is a half. All right. And I mean, okay, let me explain how I got the lambda. So I solved the Lagrange problem. And I set it to 0. Can someone tell me what the system is? Any ideas? Huh? Yeah. Is that okay? Okay. So that's how we get y equals 0. And from here, we get that x is minus lambda, but we know that x is 1. So that's how we get the lambda. All right, good. I know this problem is obvious, but I like, yeah, it's good to do simple examples. I could throw you like some 3D duality problems, but then you'll get lost. I mean, we're just trying to teach you the main idea. At the end, I have a 2D example, but I mean, yeah, I don't think you will learn more for now. Anyway, so the augmented Lagrangian is the same guy as Lagrangian plus the penalty. Okay, so you have to always put the penalty there, and you will be amazed just a little addition. It just changes the whole problem and it makes it way more doable. And we will explain why. I talked about a little bit that, you take C to infinity, and this is interesting because, so x minus 1 squared, if you take double derivative, you get 2, right? So we will prove that as C goes to infinity, LC becomes convex-like. And once you have convex-like, it's done, right? You have strong duality, you have second order conditions, you have everything, right? So that's the idea. That's why they added a quadratic term and not like absolute value, right? So, okay. All right, so set the augmented Lagrangian to 0. And let me do this with you now. So XL equals 0. So can someone tell me what the system is for X and Y? I mean, we talked about it just a few minutes ago. So what will be, what do you guys think? Rahman? What do you think? Plus what? Yeah. And then, yeah, this guy doesn't change. So if you solve the first guy, you get the thing I wrote, C minus lambda C plus 1. All right, good. All right, so what? So you see, with this penalty, you have the following phenomenon. This should be -1. So X is equal to C minus lambda C plus 1. And we already talked about, right? This is the minimizer. So compare this to 1, 0. So there's two ways to get this. Either you take lambda to -1, which is the minimizer of the maximizer of the dual. Or what else can I do? How else can I get 1? Right, so if you take limit of this ratio to infinity, you get 1. Right, so again, you got your original minimizer. Okay, I'll let that digest what happened. Okay, so yeah, so as C equals to infinity, we get this minimizer. So we have the following amazing relation that when C goes to infinity, the minimizer of the augmented Lagrangian is about the minimizer of the original constraint problem. Okay, there's no constraint here. No, no constraint. This is unconstrained. And this is constrained, right? At no point when I computed this did I use, how do you say it? I never said X is 1, at no point. Like when I did all this stuff here, I never used X equal 1. Do you understand? Is that okay? So I solved the unconstrained problem, I took its limit, and I got the constrained solution. I mean, I think that's beautiful. Like with second year calculus, you can do half our course. right? Because I just take a one gradient. You know how much work we put into this with like simplices and like boundary terms and all this crazy stuff, active constraints, inactive constraints. You just take one derivative. All right, good. So we're gonna make this more rigorous. This is not a proof. We're mathematicians. We're not like physicists. Let's wave our hands. No, physicists don't always wave their hands. Okay, anyways. So I'm gonna prove this statement. So suppose that you have a local minimizer, then the augmented Lagrangian is has the same minimizer. Okay, same guy. So by C, this is the penalty. So which is stunning if you think about it, that I don't even have to take C to infinity. I just have to take it big enough. Okay, let's go. So this is again in your book, and I want to fill in the details, get your questions, whatever. So here's a general linear algebra fact. This is outside of stuff. This is like general interest. Suppose you have a matrix that's semi-definite, so B is non-negative, and A is strictly positive on the set where Bx is 0. Now you might ask why this constraint. Remember KKT. So this is KKT, where we had that the Hessian is positive on the tangent space of all the V, where a gradient of HV is 0. That's exactly it, right? So this guy is your B. Remember, we had these constraints. Okay, but this is a general linear algebra fact. I'm just connecting it back to our theory. And we're going to prove the following beautiful fact, that even though B is non-negative, A plus CB is strictly positive, which is beautiful. So even though B can be 0, we have a positive definite. And you need this. You need positive definite to apply KKT. I know some people wrongly have answered, like in the test, they wrote that the Hessian was non-negative, but that's not enough. That doesn't give you minimizer. Okay, so please remember Hessian needs to be this. Hessian non-negative is indeterminate. Okay, so if you get equal to 0, this is indeterminate. You understand? So don't do this mistake again. Whoever did it, I don't know. Okay. All right, let's go. I will prove this by contradiction, meaning assume that for each integer k, so like a plus 2b, a plus 3b, and so on, that all these guys are not positive definite, okay? So they're not. So these are all non-negative, non-positive. All right. I mean, I don't know. I guess you can eyeball it, can't you? Like when you take C to be big, isn't it clear that you're making this guy really, really big, so that, you know, okay, anyways, we'll talk about this. But what does that mean? It means you can find the unit vector where you have this negativity. Okay, so the being not positive definite means that there is a vector, there is a direction where you have negative. Okay, all right, good. let me say this way, in some direction. All right. But it's a unit vector, so it lives on the hypersphere. So we have these directions, xk plus 1, xk plus 3. So you have all these vectors, and they live on the sphere, and a sphere is closed and bounded. Okay. Whenever you have equal sign, it means it's closed. So if you take any limit, it satisfies it, the limiting point. I don't know, whoever likes topology. And then it's bounded because by definition, a sphere contains itself. So it's bounded by 1. All right. Compactness means that there is a subsequential limit. So that means that in the space of directions, they eventually accumulate around some x star direction. Okay. Since B is positive semi-definite, you have these guys being also positive semi-definite. And now let's stare at this. Okay, this is where the meat of the proof is. So again, this is the contradiction. This is what we assumed, contradicting hypothesis assumption. And you open it up and you have this guy and this guy. All right. So, and you have that this guy over here is non-negative. All right. All right. So now, as you take the limit, so suppose that claim. This is claimed in your book but never proven. The claim is that x star b, x star is 0. Okay, it's not obvious. If it's obvious, please let me know why. So assume not. So you have x star b, x star is, I don't know, bigger than epsilon. Okay. Then what do you have? You have this sequence of xkn, b, xkn. When you take their limit, you get, by continuity, you get bx star bigger than epsilon, right? So this is just continuity. But then if you come and look at this crazy looking guy, you have the following. So what happens when I take the limit of this function over here? I want to do it with you. I don't want to just. So what's the limit of xkn, a, xkn? What is that, first of all? Yeah. So then if you add kn, xkn, xkn, this guy is also the same. So you have x star a, x star, limit of kn, and then x star b x star. This guy is bigger than epsilon. This guy is supposed to be negative, but this guy here is plus infinity. So what's the contradiction? What? Yeah, so you get, suppose this is like, yeah, 0, yeah. So you have some number a, and then you have some huge number k times epsilon, and take k to be bigger than or k bigger than I don't know, 1 over epsilon. 1 over epsilon with a. 2a, something like that. Anyhow, so that's the contradiction, that the moment you assume it to be positive, you are, yeah. Anyways, so that's it. So then you have that x star, bx star is 0, but then on this space, you have your guy is positive definite. So here's the contradiction to be done with. And that's it. Okay, thank you.